The second short lecture in Chapter 38, where we are going to continue our discussion of special properties related to the wave nature of light. In particular, we're going to look first at resolution. The ability of optical systems to distinguish between closely spaced objects is indeed limited. The two sources are far enough away to keep their central maximum from overlapping, and we can resolve them, and so their images are said to be resolved. But if those maximum overlap too much so that we cannot distinguish between them, we say that they are unresolved. This leads to Rayleigh's criterion. When the central maximum of one image falls on the first minimum of the other, the images are said to be just resolved. This corresponds to an angle equal to the wavelength of the light divided by the slit distance, or whatever aperture distance you have at that point. This kind of corresponds to where we just were in our previous lecture, where we're looking at diffraction, and we had that A sine theta is equal to m lambda for our first minimum. So if m is equal to 1, and we're dealing with small angles, so the angle theta is equal to the sine of theta for small angles in radians, then it simplifies to this. Our minimum angle is equal to lambda divided by A. So to resolve, the angle subtended by the two sources must be greater than this minimum angle. In most cases, we're going to be looking at circular apertures, and the limiting angle for the resolution of a circular aperture is a slightly more difficult problem. You have to look at the diffraction interference in a circular two-dimensional sense, and that involves solving the area disk of that interference pattern, and that gives you the first level term in the Bessel function, which is 1.22. So our minimum angle for circular apertures is 1.22 wavelength of light lambda over the diameter of the aperture. Still a very simple equation when it boils down to it. Here's an example. We have two sources, and we can see from the sources that their maximum and the first minimum are far enough away so they're well resolved. If we bring them closer together, we can just barely resolve that these are two different sources. However, if they're closer together still, then they constructively overlap, and we can see that we cannot resolve between the two sources in that case. A famous example is in 1977, the Naval Research Labs published this photo of Pluto, and what they said at that time was Pluto's moon, Charon. So Charon was discovered by this photo by the Naval Research Labs. And when I first saw this photo, I'm saying, well, how can you find something else in this photo? I mean, how do you know that there's something else there? So I have to say I was slightly skeptical, but they were proven correct. In 1995, the Hubble Space Telescope clearly resolved these two planetesimals, and here is what the Hubble came up with. You can clearly see Pluto and its moon Charon at that time. So they definitely were correct. In 2005, even higher resolution was obtained by focusing the Hubble Space Telescope on this Pluto-Charon system for 3 whole days. So they commandeered the Space Telescope for 3 whole days from all the other researchers at that time to take photos of Pluto and Charon, and they came up with a high resolution, and this is what they had. You can clearly see now the features of Pluto, the character Pluto and his little friend Charon at this point, at the highest resolution. No, actually, this is what they came up with. You can see Pluto, Charon, and they actually discovered 2 other candidate satellites, which eventually they called moons. So Pluto at that point was shown to have actually 3 moons. They're not really moons as we normally would think of them. They're just little ice balls out there, fragments of ice, but they're moving around the Pluto system. And in fact, just a couple of years ago, with higher resolution, they found 2 other moons. So Pluto has at least 5 moons, which are basically just big ice balls swirling around it. Polarization. The direction of polarization is defined to be the direction of the E field vector in whatever direction that is vibrating. It's going to be perpendicular to the direction of travel of the wave and perpendicular to the magnetic field vector. So this is what we call the amplitude of the light wave, the E field vector. For unpolarized light, we can have E field vectors going in all directions. So we have contributions of light in all directions, and this would be an unpolarized wave. A wave is said to be linearly polarized if the resultant electric field vibrates in the same direction at all times in a particular point. In other words, if it's linear directed at all times, that would be polarized. This could happen if you had selective absorption, so a material absorbed selectively in one direction and allowed it to transmit preferentially in the other direction, giving you a polarized light. Reflection. Upon reflection, the horizontal component is preferably reflected as opposed to the vertical component, giving you polarized light. Double refraction. In particular crystals where you have a different lattice structures in different directions, you could get polarized different beams. Scattering. In scattering, the molecules preferentially absorb in one direction as opposed to another, giving you a re-emitted light that is polarized. Polaroid is a material that polarizes light through selective absorption. Generally, this material is made out of linear molecules, polymers. And if you take those long linear molecules of polymers and you dip them in, say, iodine, you can make them electrically conductive, and hence they would be much more strongly absorptive along their direction of their length and transmit in between. So they'll transmit light whose electric field vector is perpendicular to the lengths of the molecules. Discovered by E.H. Land, and this led to Polaroid film. Looks like this. Preferentially absorbed in one direction, allowing the perpendicular direction to pass through, giving you polarized light in that direction. And it results in a clear resolution of the film. The intensity of a polarized beam transmitted through one polarizing sheet and then transmitted through a second polarizing sheet, which is called the analyzer, varies as I0 cosine squared of that angle, theta. We know that the E field vector is the amplitude of the light, and hence intensity is always proportional to the amplitude squared. This is called Malus's law. I0 is the intensity of the polarized wave incident on the analyzer for two polarizing materials whose transmission axes are at an angle theta with respect to one another. So it could look something like this. Here we have two polarizers. Their axes are aligned. We get maximum intensity. If we go to 45 degrees, we have a lessened intensity by the cosine squared of 45. And if we actually went to 9 degrees, we would have no transmission. Looks something like this. Two polarizers. And as I turn one, say to 45 degrees, I get less transmission. If I go all the way to 9 degrees, I get zero transmission. Come back, go to 90, zero. And interestingly enough, if I had three of them and I put them at 30-degree angles, I actually would still get a transmission. all the way through. So that's kind of a neat little side light there. Unpolarized light is incident on a reflecting surface. It's preferentially reflected in the horizontal direction because the absorption and re-emission in that direction is a little bit easier than in the vertical direction with a surface like that. So your reflected beam is going to be preferentially polarized in the horizontal direction and may have some vertical reflection as well. The refracted beam will also be partially polarized as a result. If you're able to adjust the angle of your incident beam so that the reflected beam is perpendicular to your refracted beam, an interesting result occurs. This is a special angle. We're going to call it our polarizing angle. And we'll find that at that point where the reflected beam is perpendicular to the refracted beam, the reflected beam will be completely polarized. Snell's law still applies to this situation for the refracted beam. In other words, N1, the sine of our incident angle, our polarizing angle in this case, is equal to index 2 sine theta 2, where theta 2 is our refracted angle. But since there's a 90-degree angle between the reflected and refracted beam, if we look at the geometry of this diagram here, 90 degrees between the reflected and refracted beam, that means theta 2 and theta polarizing, theta sub p, are also add up to 90 degrees. They are complementary. So theta 2 is equal to 90 minus theta sub p, and that means that the cosine of theta sub p should equal the sine of theta 2, which is 90 minus theta sub p. So I'm going to substitute in for the sine of theta 2 the cosine of theta sub p. And if we divide both sides of this equation by the cosine of our polarizing angle and divide by N1, we would get that index 2 divided by index 1 is equal to the tangent of this polarizing angle. This is called Brewster's angle. If we actually we're going from air to, say, glass, air being an index of refraction of 1, then we would have that the index of refraction of that material, N2, would equal the tangent of the polarizing angle. So if we change our angle to the point where the reflected beam is totally polarized, then the tangent of that angle would be equal to the index of refraction of the material, and be one way to determine the index of refraction of a material. Kind of neat. When light is incident on a system of particles, the electrons in the medium can absorb and re-radiate that light. This process is called scattering. Scattered sunlight reaching an observer on Earth will be polarized. The horizontal part of the electric field vector in the incident wave causes the charges to vibrate horizontally. The vertical part simultaneously causes them to vibrate vertically. But they'll be re-emitted as you're looking up. You will preferentially see the horizontal component as it's coming down to you. Hence, you will see a preferentially polarized light out of the air. Short wavelengths, violet, are scattered more efficiently than long wavelengths, red, in our sky in terms of the visible spectrum. When sunlight is scattered by gas molecules in our air, the violet is scattered more intensely than the red. Hence, we should expect to see that the sky was violet. But our eyes are more sensitive to the blue, so right next to the violet is blue. So you see blue instead of violet, but they're both being scattered more, and that's why the sky is blue. At sunrise or sunset, you're looking through more atmosphere as you're looking across the curvature of the Earth. There's a lot more atmosphere to look through, and the blues gain scattered before it actually gets to your eyes. So actually what you're going to be left with is more of the red color. So as you're looking at sunrise or sunset, the blue is scattered away, leaving the light at the red end of the spectrum, making it to your eyes, and hence sunrises and sunsets are reddish and orange on that end of the spectrum, because that's what makes it to your eyes. This concludes the second short lecture in chapter 38 dealing with